In this video, I want to show you some things about the homeworks from day 4, and I want to show you a number of examples from the homeworks that I counted correct, and also give you some feedback on ways to save time or also just what was necessary to get the credit. My real goal is that these videos and sketches be helpful to you and that they help you learn. And so how long should they be? How much detail? Whatever helps you learn. But there are going to be ways you can be more efficient. So let's start with this one up at the top. This one nicely described everything. Things I like about it, the actin microfilaments here, this person did just a few of them and then did a line with an arrow. That arrow, in this case, likely means two things. One is that the circles continue, but in this case it could also mean movement, but I think it's the brown arrow that meant that that whole actin filament moves. The myosins are shown here against the membrane. I would have loved it if the person had shown a little protein tethering it either to the membrane or the cytoskeleton, but not. If it was tethered to the membrane, it would also need to be tethered to the cytoskeleton. Membranes alone, if there's not connections to cytoskeleton, are like soap bubbles. They're very weak. Showed the same thing down at the bottom, and then here's where they showed the power stroke. So if we zoom in, here's the myosin. Here's the attachment to the actin. Again, they've just shown 3, saved a lot of time by then continuing it as a line. Here's the power stroke, goes into a new position. And they could have shown it with just 1 or 2 myosins. This one is probably not necessary, and even you can argue the second one is not necessary. And then as this moves, and especially as the myosin repeatedly attaches to further and further back actins, it'll push this, creating force on the leading edge. Was this text necessary? Nope. They could have done 1 and shown an arrow here to that, and I would have known myosin was attached. They could have shown 2 and this arrow here, and I would have known it's the power stroke. And then 3, they could have just shown the arrows pushing against it. Is the text useful? Sure. Labeling something on an exam could be helpful. But when you're practicing for yourself, you may not need all of it. And you're welcome to condense to save time. In fact, condensing can not only save time, it can make it easier for you to think through it. The fewer things on there, the easier to think. This was another full credit one. There's only one thing I would have recommended be changed, and that was tethering the myosin to cytoskeleton or the membrane. Almost nobody did that tethering because it wasn't in the videos, and well, it was, but I didn't really talk about it in the videos. This one adds something, which is fine, but wasn't necessary here. This one regulates it with tropomyosin. Here's the tropomyosin, which normally would be blocking all these binding sites for actin. But when calcium binds, here's a calcium bound to troponin, not labeled, but doesn't need to be, then that causes a change in shape. The +2 charge of the calcium causes the troponin to change shape, and that shifts the attached tropomyosin down off these binding sites. So here's another troponin further along. And that allows the myosin to attach. We have a power stroke, and then that moves this whole thing. Here is, I think, the edge of the membrane. It's pushing against the membrane and going to extend a pseudopod. So this also was a good full credit answer. Here's another one. And whoops. Here's another one. And this one it's great. It's got all the stuff it needs. It shows the power stroke. It shows the actin, shows very clearly it pushing against. Love these little dotted circles here. But this one could have been just a couple of circles, maybe a couple here, and then just a line, and then maybe a couple at the end, and a couple of the dotted ones. So save yourself time. Don't put anything you don't need in the sketch. Do you really need to say push forward if you've got those arrows in there? Not for me, and probably not for you. Do you need to say actin microfilament? That's up to you. Maybe writing it out helps you remember it, in which case you want to put it. But maybe you want to abbreviate actin MF. And then pressure on leading edge. Do you need that for me? Nope. Myosin attached. And this person did have the myosin attached to other myosin and cytoskeleton. So that means it's going to be attached to the rest of the cell, but it'll push the front. So this is a really good one. Could have been a little more efficient if the person wanted to be. Here's another one, full credit. This one is a lot more like my handwriting, which I like it. It's got I'm not sure that's a compliment, but here are the myosins clearly attached. Here's the actins. They're labeled here and showing this long chain and then pushing. And this is the before. Here's an arrow. Clearly the arrow means time right here. And here's the leading edge. You can tell the leading edge has gone out further. Notice the use of arrows. Arrows mean really different things in different contexts. So here, the arrow is a label. Here, the arrow is movement and pressure. Here, the arrow is time. So in this little bit here, there's 3 different meanings for arrows. And you should keep that in mind as you're developing your own, what's called visual literacy for making sketches. For 2, we want retraction, so we want pulling forces. This one's the same person. I like this, a really nice simple sketch. They didn't bother relabeling it, don't need to. It was labeled up there. So here's our actins. Here's the myosins. Notice they've flipped the orientation. So now the orientation is like this. And so the power stroke is going to do this. And they did not bother to show the power stroke again because they just showed it up here. So they flipped the orientation. Now the power stroke is going to go this way. And what they didn't show that I would have loved is some kind of attachment to the trailing edge so that as the actins move, it pulls along the trailing edge. I didn't show that in the video, so not so critical, but there must be some kind of attraction for this attachment for this to work for retraction. Here's another one. Again, you can see the orientation of the myosins are now this way, so the power stroke is going to go like that. Here is the power stroke showing the movement, and we're going to pull away from the trailing edge. And that's what these green arrows are showing. What about assembly and disassembly of microtubules? This one is partly in a sketch and partly in Word. They didn't actually show any microtubules being disassembled and the cargo moving along, but they said, and I accepted this as a label, microtubule disassembly and microtubule assembly, and then also new actin filaments, so presumably microtubule assembly proteins, microtubule disassembly proteins. They show dyneins and kinesins, I think with the correct orientation. I am not going to be concerned that you remember which way dynein goes and which way kinesin goes, especially since it's not consistent across all cells. They've taken it past the microtubule organizing center, which is fine, but I didn't really need that for this particular one. This gets the point. Here's another one, fairly similar. They're showing disassembly, assembly, and as you assemble new ones, as this leading edge of the membrane is bouncing back and forth slightly in response to random molecular motion and heat, you can assemble new microtubules or microfilaments behind it and stretch it out. Another example, so these are all really similar and all got full credit. Again, notice there are multiple ways to do it. I'm not looking for one simple one. And then for the next one, osmosis, lots of ways to show it again. So I've just picked out a few. Here is water that is not attracted, not bound to anything. And here is water, not particularly strongly bound, but bound to sodium, chloride, and chloride. And so there's only one free water here. So with all free waters, the blue, then there's no net movement. We've got 5 waters on this side, 1, 2, 3, 4, 5, and 5 on this side. No net movement, they're gonna leave and enter at the same rate. But in black here, when these are attracted to chlorides and sodiums, now water is gonna be in the hydration shell. It's not free, only this one water that's been circled is free, that's in the black. And that's the only one free to go this way. You've got 5 times as many chances for a water to go this way, only 1 in 5 this way, so you're gonna have net movement. These others all show the same thing in one way or another. Here is no net movement, same number on both sides, so same probability. And here's what happens when you have sodium, and see the hydration shell here. Let me zoom in a bit. Hydration shell around a sodium, around a chloride, around a chloride, around a sodium. And so there's just a handful of free water molecules. And even though there's many fewer water molecules on this side, some of them are going to go through. And you'll have net movement toward the area of higher solute concentration. There's some description down here. There's an image of a hydration shell, nicely shown around sodium. And the positives, very weakly positive, just slightly more positive than negative hydrogens around chloride. Electrons are spending a little more time around the oxygen, so the oxygens tend to be a little bit more negative. So here's our hydration shells. And then some text. Now, all of this detail was not needed. A much, much simpler version that included really just some version of this and some version of this would have done it just fine. But if this helps the person who's doing the sketch, then absolutely, it's worth it on the first time. But if you're practicing a sketch, like if you're doing it on summary sheets, you might have this on your first version. If your first one has this much, I would be fine on your second summary sheet if you're going to do that exercise to cut it down to something much simpler. And even with fewer, if you have this sodium and this chloride, do you really need this one and this one to make the point? Or could you just do it with that? So here's a couple more. That this time hydration shells around calcium. And so you're going to have net movement, many more chances to go this way than this. And even when there are fewer total waters on this side, you're still going to have them moving. Here's another one showing equal, in this case, it looks like distilled water, but could be equal solutes on both sides, equal probability for these three. Put some sodiums over here. These waters are not available, and you're going to get water moving. What I would have liked in this one is an arrow showing the net movement of water toward the area with all these solutes, because these 5 are free to move. This one is not. Biological glues and gel salt transitions, every one of the 12 that I graded looked good. The main thing I wanted to point out here is, again, you decide how much you want to add. This was really nice and thorough. It showed hemidesmosomes. It says desmosomes, but a hemidesmosome connects a cell to something outside the cell. So hemi would be better, but this is really nicely detailed. And a hemidesmosome is just a half desmosome. So the structure is the same. It's just that it doesn't have the other half here. Okay, so they're showing the secreted mucus of some kind, or the glue matrix. A lot of different compounds will do it. The key is often that they have this branched structure. They have an uneven, or they have a mix of charges, so they will adhere to different substrates. They can be net positive or net negative, and that affects which kinds of substrates they adhere to. And all these loose strands mean that the loose strands can wind up in different locations, matching the positive and negatives. And then you can either branch them with positive calciums. I think that's what these green pluses are, although I would have expected them to be +2, or maybe in this one they're just showing the quinones. So the small molecule that easily forms a covalent bond on each side does take some, it is a reaction that requires a little bit more, but details aren't so critical. Lots of things do it to make quinone tanned or quinone cross-linked proteins or other strands. And we'll talk much more about this type of cross-linking to stiffen up either extracellular matrix, because you can do it with collagen in tough skin or integument. So some animals do it to harden their skin or integument. Here's another one. Again, I would suggest, would this be enough, showing the water leaving as the cross-linking is happening, and it tends to start shrinking this down because the cross-links restrict movement, and so water leaves, and you get cross-links and you get a good glue. Here's the quinone as a covalent bonding molecule, connecting strands, pushing out water, hardens into glue. So these are showing the steps, which I like, but probably did not need this whole part. So feel free to limit it to essentials. I am quite good at looking at something and going, yep, you've got the essentials. And it will save you time both when you're doing the studying, when you're thinking, and also on exams. Okay, the last, the other parts I'm not going to show, and feel free to email me if you have questions.